much of what we're covering today is review. We'll get into some new material on Friday, but there's a fair bit of review today, and I think it's important review. So what I was saying earlier was that, again, I don't think I need to work very hard to rationalize why you need to know about carboxylic acids. That those functional groups show up all the time in synthetic intermediates used in industry for making pharmaceuticals and other molecules, also for making polymers of various kinds. Carboxylic acids, the carboxylic acid functional group is very, very common. Just to give one example, certainly every amino acid molecule is a carboxylic acid functional group, at least until it's condensed to make the amide linkage or the peptide bond. There are carbohydrates that have, or carbohydrate derivatives, I should say, that have carboxylic acid functional groups. Some of these are pretty important. Your aldaric and aldonic acids. We'll get to them when we do the chapter on carbohydrates. And of further importance, we're doing the chapter on lipids next in terms of which biochem chapter is next, because a goodly fraction of fat-soluble molecules are nothing more than carboxylic acids with very, very long alkyl chains. So a lot of them look something like this, except R is really, really, really big. So the point being, if you understand about carboxylic acids, you've got good background to understand the behavior of most of the lipids. So that's how we're going to do that one next. So that's carboxylic acids. Nitriles, I have to be honest, they don't show up all that much in biological systems. I can't say never. I can't say not at all. You know, you've got your cobalamin and cyanocobalamin, which are related to vitamins. And so those will have, at least the cyanocobalamin will have the cyano group in it. I mentioned these, where are they? These cyanogenic glucosides. These are things that you'll find in a lot of natural defense mechanisms, but you find these things in very small quantities in apple seeds and in the pits of a bunch of related fruits. So peaches, plums, cherry pits, nectarines would certainly have these things too. And my understanding, as you know, I'm no biologist, but my understanding is they're part of a natural defense mechanism. And if your mother was like mine, who warned me not to eat apple seeds. I don't think I was really getting into much of a habit of that, but at some point she warned me not to eat apple seeds because they're bad for you. If your mother said that to you, then she, like my mother, was right, because that is correct. Now, at the same time, I don't want anyone to panic. You know, it's not like if you swallow a couple of apple seeds, you'll die. No, it would take probably, you'd probably have to measure in pounds the amount of apple seeds you'd need to eat in order for it to have any ill effects. And in terms of peach, plum, cherry, nectarine pits, I doubt there's very many people who find those things delicious and are looking forward to eating them anyway. But they are there. There are these things that are derivatives of carbohydrates, but give off cyanide ions when exposed to stomach acid. At least that's my understanding. Like I said, I'm no biologist. In terms of nomenclature of carboxylic acids and nomenclature of nitriles, it's pretty straightforward. If that's why I always like to say, if you can name alkanes, that's probably somewhere between 85 and 90% of what you need to know to name anything in organic chemistry. And I would say further, if you can name alcohols, you probably have now somewhere between 95 and 100% of what you need to know to name anything else in organic chemistry. So, so I think you can manage that very well on your own. Of course, when you get to the section on spectroscopy, we haven't covered proton NMR yet. We will later on, but we have covered carbon-13 NMR. And certainly carboxylic acids and nitriles stand out pretty clearly in an IR spectrum. Again, I don't have exact numbers committed to memory, but I believe you'll find the nitrile carbon-nitrogen triple bond stretch, if I recall right, it's around and about 2,200 wave numbers, give or take, and there's very little else that shows up there. Carboxylic acids, of course, you remember, the ones with hydrogen bonding in their OH groups, you get that big, ugly, ragged, unsymmetrical looking OH stretching resonance. It's not rare for that to more or less obliterate the entire high frequency end of the spectrum. So those stand out pretty easily. Of course, you've also got the carboxylic acid carbonyl stretch. That being said, one major topic I want to cover today, even though it's kind of review, but it bears repeating, is ideas involving the structure and properties of carboxylic acids. Certainly, let's refresh our memories on acidity and what are some factors that lead to greater or less acidity in this or that particular case, and other ideas involving the structure of carboxylic acids. I do have a reef pulling session ready for you guys. Probably after that, we'll take a little break and do our reef pulling session. And then I want to end up with, let's see, what I want to end with is, there's the acidity business. As we have time left at the end of class, technically preparing carboxylic acids is going to be next class, but I sort of, wrote down some things for you guys to get down and review before next time, since a lot of that is review also. So that's basically my plan for today's class. So what can we say about the structure of carboxylic acids? Well, certainly I would hope it's to no one's surprise at this point that the carboxylic acid carbon is sp2 hybridized. It needs to be in order to accommodate the pi bond between carbon and oxygen, and in order to accommodate that trigonal planar shape that we find at such an atom. We've already spoken about a resonance contributor that looks something like this. Those are common to all carbonyl compounds. But in the case of carboxylic acids in particular, there's yet a third resonance contributor, which looks something like this. And again, a reminder not only for you guys, but also for myself as well. Remember, there's no flipping back and forth here. This is not an equilibrium. The true structure of any carboxylic acid, regardless of what R is at all times a mixture of those three structures. There's no time averaging going on. It's just at all times a hybrid of those three structures. Certainly, that structure is going to be by far the major contributor to the overall molecular orbital picture. This one also plays into it, though, and is the reason why carboxylic acids have an electrophilic carbon atom. The carbon atom is electrophilic, as in every carbonyl compound, but the function of this structure also being in the mix. Look what that structure does to the plus charge. It takes it off of the carbon atom and shares it with the oxygen atom. So to whatever degree there is any amount of plus charge on the carbonyl carbon in a carboxylic acid, it's spread out over the carbon and the oxygen. And so that means that as carboxylic acids go in terms of electrophilicity, carboxylic acids are pretty much at the bottom in terms of reactivity towards nucleophilic attack. And we'll get to that eventually. I anticipate we'll cover that in chapter 21, where we'll actually go over like an order of reactivity, pretty much all of the so-called acyl derivatives, all of the different types of compounds that you'll find with a carbonyl group in there. We'll have an order of reactivity of, you could go from least reactive to most reactive to least reactive. However you do that, I think you'll find that carboxylic acids are pretty much at the bottom in terms of reactivity, because carboxylic acids have less plus charge on that carbon than, certainly than, let us say, aldehydes or ketones. you're not going to be able to get a resonance form like this with an aldehyde or ketone, right? So that's why carboxylic acids are relatively unreactive towards, or relatively unreactive by nucleophiles. They're still a little bit electrophilic, but less so than other carbonyl-containing compounds. So another interesting feature of carboxylic acids, at least for smaller ones, is they tend to form these dimers, which look something like this, and involve two intramolecular hydrogen bonds. And the effect of all that is in order to make the carboxylic acid change state, either from solid to liquid, what we call melting, or from liquid to gas, which we call vaporization or boiling or a bunch of other things, we have to disrupt these hydrogen bonds. Again, we're not breaking covalent bonds, of course, but we have to disrupt those hydrogen bonds, and that takes energy in the form of heat in order to do that. So it's no wonder that melting points and boiling points are higher for carboxylic acids than for other molecules that don't have that hydrogen bonding, but of similar molecular weights. And I would say that's true until R starts to get pretty big. Anything above maybe, I don't know, 7, 8 carbons or something like that. Then you might start to have trouble forming these dimers. But then, of course, you're going to start getting higher melting points and boiling points for other reasons, just because the molecule's getting heavier. But that's an interesting structural feature that of carboxylic acids, I would say. The other one I should mention in terms of physical properties of carboxylic acids, you've probably all experienced this, at least to an extent, is that they really generally don't smell very good. You've certainly all smelled acetic acid, which is in vinegar. Vinegar is generally round and about, depending what kind, what brand, but round and about 4 to 5% acetic acid. But most, at least of the smaller to medium-sized carboxylic acids, smell very disagreeable like that, and you can tell that in some of their trivial names or common names. For instance, the 4-carbon carboxylic acid, so where R is a propyl group, you can certainly call that butanoic acid, right? Butane, butanoic acid. That's fine. Everyone will know what you mean. It's also called butyric acid, B-U-T-Y-R-I-C. And that's because you find butyric acid in rancid butter. Probably we don't really experience that much these days since we have such things as refrigerators. But you can imagine how unpleasant butter that has gone bad must smell like. Add another 2 carbons to make hexanoic acid. So R is a pentyl group in that case. And again, there's nothing wrong with calling it hexanoic acid, perfectly acceptable. But the trivial name of hexanoic acid is caproic acid, C-A-P-R-O-I-C, which comes from the same root as Capricorn the goat, because it smells like billy goats. So you're getting the idea. These things do not smell good. That tapers off once R gets sufficiently big that the molecule just is no longer volatile. And because if you can't get any molecules of it into the gas phase to go up your nose, then you're not going to smell anything. And generally around pentadecanoic acid or somewhere, plus or minus around there, it's usually about where you stop being able to smell them because they're just so high melting and let alone boiling that you can't smell them. Good. So that then gets us into the idea of acidity of carboxylic acids, which I'd like to spend a little bit of time on at any rate. Let's see what we got here. Good. Any questions about any of this so far? Just want to kind of move this so that it fits on the screen. Being overly picky here. Well, we've already discussed acidity a little bit. And one of the points that we've made even starting in first semester organic, is that anything that you can do to stabilize a conjugate base makes its conjugate acid stronger. And that makes sense, because anything you do to make the base happier, more stable, means that the acid is going to be more willing to give up the proton, because the stabler its conjugate base is, then the more energetically favorable it is to lose the proton. So that's what we measure with these with both Ka values and pKa values. Now, again, I'm not real interested in you guys memorizing certainly large lists of pKa values. I think if you're aware that alcohols and water, the pKa in the mid to upper teens, and if you know others relative to that, I think you're going to be in pretty good shape. But these structural and stability effects on pKa can be very dramatic, actually. And one classic example that we probably gave is comparing the acidity of ethanol to the acidity of acetic acid. And this is otherwise a very fair comparison. Both of them have 2 carbon atoms. Both of them involve an acidic proton attached to an oxygen. So it's a very good comparison. And what we find is that the difference in acidity is very dramatic. Ethanol, like pretty much all other aliphatic alcohols, has its pKa of 16 is very typical, whereas acetic acid has a pKa that's much lower. Even if we call that 5, that's 11 orders of magnitude. So we would say that acetic acid is, let me see, 100 billion times more acidic than ethanol. And there has to be something that's causing that. And what that means is that another way of saying the same thing is that the conjugate base of acetic acid is some 100 billion times more stable than the conjugate base of ethanol. And so in order to understand relative acidities, let me see. I think we're fine. This is a minus charge over here, if that's what you mean. So that's the ethoxide ion. Bottom oxygen where? Oops, that could be a problem. Yeah, we don't want oxygen to have 10 electrons. That'd be bad. There we go. Thank you. Now I think we're good. In any event, so there has to be something that's making this conjugate base that much more stable, to the tune of 100 billion times more stable than the ethoxide ion. Before I get to that, I also want to remind you, remember that pKa values always and only refer to acids. It's not correct to talk about the pKa's of bases. That doesn't work. It's the acid dissociation constant. But the thing that's difficult, the main difficulty here, such as it is that when you're thinking about the acidity of some compound, you need to think about the structure of its conjugate acid. So you need to be able to imagine in your head the structure that you get when you remove a proton. Here, for this first example, I'm giving that to you because I want to be as visual as I possibly can. Later on, I'll actually challenge you a little bit more here. But you need to be able to picture what the acidic species looks like with 1 fewer proton. And you need to be able to pinpoint in your mind where that acidic proton is coming from. In this case, they're both coming from oxygen atoms. Make sense? That's what you need. That's what you need to be able to do in order to know what you need to know here, in order to understand the effect of structure on acidity. Once we do that, I think it becomes pretty obvious that, yes, again, with obeying the octet rule, thank you, that the acetate ion, the conjugate base of acetic acid, is stabilized by resonance. What that means is that this minus charge in the oxygen is delocalized. It's spread out and shared between these 2 oxygens. If you wanted to think of the true overall structure of the acetate ion as having a -1/2 charge at all times on both oxygens, I am okay with that. That's not wrong. I think that's a perfectly reasonable way of thinking about it. And remember that like charges repel, so in spreading out that minus charge over multiple atoms, you're allowing the minus charge to spread out more, so you get less electron-electron repulsion. So that's why in these cases, these resonance stabilized conjugate bases mean that we get a significantly more acidic conjugate acid. The minus charge in the oxygen in ethanol is now localized on that oxygen. Granted, we're much better off putting that minus charge in an oxygen than on most other atoms, right? Oxygen is highly electronegative. Certainly much better to put a minus charge in oxygen than, say, on nitrogen or carbon, certainly. But still, there's a dramatic difference between the minus charge being localized on this oxygen versus delocalized, spread over multiple atoms. It means that when the minus charge is localized, it has less surface area, if you will, to spread out over. And so the minus charge is more close in, and there's more electron-electron repulsion as a result. And that alone is enough to explain this 11 order of magnitude difference in the acidity between two otherwise very comparable molecules, both of two carbons and both of the acidic hydrogen coming off of an oxygen. So that's otherwise a very good comparison. So that type of comparison is very typical, but you need to be able to imagine the acids with that proton gone and think about the structure of the conjugate base. Memorizing numbers is not going to do it here. You need to be able to think about structures and compare them in terms of stability. And I think you'll find, especially when you get these very dramatic changes, I think you'll find it goes back to something very fundamental, something involving resonance, something involving the inductive effect, which we'll get to in a moment, or even something involving atomic size. Just to give you another example that we could make the same type of argument, what if we compared ethanol to ethane thiol, CH3CH2SH? And this is something we talked about back in chapter 17 last term. We compared the acidity of alcohols and thiols, with, again, other things being equal. And I don't have the exact pK of ethane thiol off the top of my head. You can certainly look that up. I anticipate, so here we're talking CH3CH2SH versus CH3CH2OH. I think you'll find the pK of ethane thiol is, I would say, rounded about 9 or 10, somewhere in that general zip code, which again is a big difference. We're talking about a difference of being maybe 1 million times more acidic than ethanol. And there we would have to credit the difference in atomic size for that. Remember, in both cases, for the conjugate base, you have the minus charge localized on an electronegative atom. But if you think about the sulfur atom, that's now this big fat atom that you've got all that surface area to spread out the minus charge on when you make S minus, as compared to the oxygen atom, where it's going to be closer in together because you have a much smaller atom. But I think you'll find acidity comparisons, and if you want to know how it will look, again, I think you'll get lots of practice, or at least some practice, on the OWL assignment. But I think you'll find when it comes to comparing acidities of acids, of course, without using any data or without needing to memorize any numbers, I think you'll find that it comes down to something very fundamental, something like resonance, certainly, the inductive effect, certainly. We'll do an example of that one next, and maybe even atomic size. So one other set of comparisons I want to go through involves the inductive effect. What if we compared acetic acid to what we would get if we one by one replaced the hydrogens on the methyl group with very electronegative fluorine atoms? And of course, I want to stress, these numbers I don't know. Well, I might know acetic acid is 4.76 by now, just by having to write it down so often. But these other ones I wouldn't have known. I had to look them up, and I wouldn't expect you to know them off, these pKs off the top also. But I think you can see a very clear trend when we're comparing the acidity of acetic acid to fluoroacetic acid to difluoroacetic acid to trifluoroacetic acid. These pKa's are getting smaller and smaller, corresponding to stronger and stronger acids as we replace one by one the hydrogens in the methyl group with fluorines, with electronegative fluorine atoms. And even changing just one hydrogen to a fluorine makes a pretty dramatic difference. So again, you're going from 4.76 to 2.6. Again, don't forget, that's a factor of 100. So fluoroacetic acid is round and about 100 times more acidic than acetic acid. And after that, replacing further hydrogens with fluorines gets you around an order of magnitude, around a factor of 10 in acidity. And again, that's not surprising. But in order to understand this, you need to be able to think about the structure of the conjugate base. And here I'm challenging you. Here I'm not giving you those conjugate bases. I'm going to make you imagine them in your head, which is hard. That takes practice. But I think you can do that. You can make the same changes as we did to go from ethanol to ethoxide, from acetic acid to acetate. So I think with that, you've got enough information to imagine what all of these conjugate bases look like after losing that acidic proton. And in all cases, well, you get anions, first of all, but imagine replacing one of these hydrogens with a fluorine. This thing's now sucking electron density like mad, right? Fluorine's the most electronegative element we have. So that's going to withdraw some of the minus charge in the conjugate base when you go from CO2H to CO2 minus. That's now going to be an anion, but that fluorine is helping to withdraw some of that minus charge toward itself. So once again, we're spreading out the minus charge more. You've got less electron-electron repulsion due to that minus charge being spread out over a larger surface area. And that only increases when we go to 2 electronegative fluorines and then to 3 electronegative fluorines. That helps to stabilize that minus charge even more, this time though not by resonance, but by the inductive effect. This is otherwise a very good series. It's always best if you can keep as many things the same as possible. Now, we have ways of comparing things when they change 2 things on us. But, you know, if you change hydrogen to fluorine and the carboxylic acid to a sulfonic acid and go from alkyl to aromatic, after a while, there's so many moving parts that it becomes hard to make the comparison. Generally in science, when we're actually studying the effects of structure on something, generally we want to make as few changes as we can in order to isolate the idea that we're looking at. Delocalized electrons is more acidic. Let's say delocalizing the minus charge in the conjugate bases means that you're making the conjugate base exactly more stable, which means that you're making the acid more acidic. So you're not wrong. I just wanted to be a little more specific about that. But the reason it works like that is you're spreading out that minus charge in the conjugate base. And the more you can do that by any means, whether by resonance, whether by the inductive effect, whether by atomic size, like in thiols versus alcohols, whichever method you use to do that, that's going to make the acid stronger by making the conjugate base more stable. Again, other things being equal. In all of these, I feel like I've isolated just one structural characteristic, so that as much as possible, other things are equal. So one word answer to your question is yes. You know, that's basically how it works. But I want you all to understand why that is. And I'm not saying you're doing this, but I want you to understand why it is, as opposed to memorizing a sentence. You need to be able to apply that in situations that maybe you haven't seen those exact molecules before. Certainly, I don't expect you guys to memorize any pKa values. It's good to have an idea of where the different functional groups show up. I think you'll find, if you are fair about it and look at a bunch of carboxylic acids, in general, in the absence of other functional groups besides that carboxylic acid functional group, I think you'll find most functional groups, or most carboxylic acids, have a pKa round and about 4 or 5. That's very typical. Just like alcohols are right around the same area as water. Water's around 16, and most aliphatic alcohols are 16, 17, 18, somewhere in there. Except, of course, for phenol, there's another one. Phenol, of course, is hydroxybenzene. You know that, you learned that name in chapter 16, I think, maybe 15 or 16 when we did aromatic compounds. And that's another one that we talked about in chapter 17. We explained why phenol and substituted phenols are special. I could have given that as an example here too. So you might want to review that from chapter 17. If you compared phenol to ethanol, again, I think you'd find the pK of phenol is round and about 10, give or take. And there's a very good reason for that. And we covered that back in chapter 17. So you might want to go back and refresh your memory on that. But there are always, so it would seem, very fundamental ideas like this. Good. Well, then, of these 5 choices, you may or may not get a cis alkene, but that's not going to be one of the driving forces. I'm not sure we even get the beta-ene. A question about getting credit for, I'll tell you what I'll do. Let me write down your name and I'll just waive it for you for today. So it won't count against you. But ordinarily we can't make exceptions like that. But it doesn't really matter. But things like this happen. Sometimes the thing just doesn't work. And so, that sometimes when back when we did this in person, someone's clicker unit will malfunction. Things happen. And that's why I'm going to drop at least the lowest 30% or 25% or something like that. 25, I guess, whatever's in the syllabus. Good. So let me not waste any more of your time. I hope we made it clear that it's forming that phosphorus oxygen bond, actually first one and then second one. That's the major driving force. Certainly 4-member transition states and intermediates are not favorable, but it's forming that phosphorus oxygen bond that allows us to do that in spite of those things being so unfavorable. So in any case, I think B is the best answer, as did you. And last but not least, which of the following is most likely to add directly to the carbonyl group of an alpha beta unsaturated ketone? Well, I would say the cyanide ion, as well as water and alcohols, as well as primary and secondary amines. We even gave some examples. These are ones that will add to the beta carbon of an alpha beta unsaturated ketone or aldehyde. As for tertiary amines, those are not going to add to either carbon, at least not irreversibly, right? You won't get any kind of stable compound out of that. It'll just revert back to starting materials. Only Grignard reagents, and of course alkylithiums, will be the ones that will prefer to add directly to the carbonyl carbon. Those, along with your hydride reagents, are the only ones that, given a choice, if they see an alpha beta unsaturated ketone or aldehyde, will hit the carbonyl carbon directly. So I think A is the best answer. So let's do this. Carboxylic acids. One of them is oxidation of alkyl benzenes. Potassium permanganate. And if you want to review that, you can find that in 16.8, not 16 to the power minus 8. The fact that they used a dash here instead of a period causes endless problems. What a dopey decision. Anyway, that's one. We discussed that you can make benzoic acid derivatives that way. There's also, and we'll go over these more in detail next time. The other one is oxidation of a primary alcohol. Well, let's say of an aldehyde or primary alcohol. Generally with something really strong like Jones reagent. That's basically chromic acid. So it takes really strong oxidizing agents. That's in chapter 17, specifically 17.7 and 19.3. And I think all of those are in your class notes as well, but we'll maybe get them all down here, at least in words. And then maybe we'll do a couple of examples of these next time, just to remind you of these reactions, because again, at least 3 of these 4 reactions are older. There's also carbonation. They sometimes also call it carboxylation of a Grignard reagent. Or I mean, you could certainly also use or an alkylithium. And basically it just involves, we'll go over this with some examples next time, but basically it just involves adding nothing other than CO2, carbon dioxide, to a Grignard reagent. Or again, recall for our purposes at least, and really for pretty much any other purpose I could think of, Grignard reagents and alkylithiums are interchangeable. Whatever you can do with one, you can do with the other. And you can read about that in 10.6 and 10.7. And so we've covered that reaction already. Rather than adding the Grignard reagent to, well, 10.6 and 10.7 will remind you of what Grignard reagents and alkylithiums are. We had a little more to say about this type of reaction, I would say also back in chapter 17, since there are ways of making alcohols. But if instead of using an aldehyde or ketone, so actually you could even just go back to the previous chapter. So I'll even say, also see relevant in both 17 and 19. Since we just talked about adding Grignard reagents as well as hydride reagents to aldehydes and ketones to make alcohols. So that's a reaction we know already. The only twist is what we're going to add rather than an aldehyde or ketone is CO2. And if you work it out, if you add CO2 and then acidify it, you'll get a carboxylic acid. So like I said, we'll go over examples next time. And last but not least, hydrolysis of nitriles. And hydrolysis of pretty much a whole crap ton. Can I say crap ton here? A whole crap ton of, probably that's fine. I probably shouldn't go to anything stronger than that though. But certainly hydrolysis of nitriles will give you the corresponding carboxylic acid, corresponding meaning that it is the same number of carbon atoms as the nitrile. And in fact, the nitrogen in the nitrile winds up in a molecule of ammonia. And we're going to go over the mechanism in more detail in chapter 21. But we'll give some examples of that type of reaction next time.